we've learned about vectors and we've learned about kinematics and motion in one dimension. Now we're going to combine these two concepts when we talk about motion in two dimension. And we're first going to talk about what a projectile is, and then we're going to talk about two types of projectiles. Projectiles that are launched horizontally, like you're shooting a gun or shooting an arrow, or projectiles that are launched at an angle, such as kicking a ball up in the air or shooting a basketball. So let's get started. So what is a projectile? A projectile is anything that is accelerating due to the force of gravity. So it is just like an object in free fall. It is an object in a free fall. It could be a ball dropped. It could be a ball thrown. It could be a kickball in the air. But the most important thing is to consider it when it is only being acted by gravity. So there's no air drag. Only gravity. And gravity is acceleration due to gravity, and it's negative 9.8 meters per second squared, and it's acts downward, not to the left, not to the right, not up. You pick up speed as you fall down towards the surface of the earth. So let's imagine a ball that we are going to do some experiments with. So we're going to, first of all, imagine throwing a ball with no gravity. If there was no gravity and we threw something forward, right, at some initial speed, and there was no gravity, and there was no anything acting on it, it would move at a constant rate forward. So let's draw a motion diagram so we can show that constant speed forward, whatever speed. We threw it at 20 meters per second, that's what it would do. What if we instead turn on gravity and we just drop it from rest? So if we do that, if we drop it from rest, then the initial speed is 0, right? And it picks up speed by negative 9.8 meters per second every second. So it's picking it up in the downward direction. So it would fall, and it would fall, and it would fall, and it would fall. It would get further and further and further, right? So it would have some acceleration in the y direction. So in the y direction, the acceleration is gravity. And when we just throw it, when there's no gravity, the acceleration is 0. So what happens if we actually throw it forward and there is gravity? Well, it would move forward at a constant rate, right? But it would also drop. So it would move forward at a constant rate, but it would drop. Oops, that doesn't look good. Let me fix that. It would drop. And if we trace that path, right, it would look like a parabola. So it would move forward at a constant rate, but it would accelerate downward. So it has two types of motion. It has a forward motion, right, a Vx, and it has a Vy. The Vx is always the same, but the Vy is picking up speed. Vx is always pushing forward at a constant speed, but the Vy is going every second, getting bigger by almost 10 meters per second in the down direction. And then, of course, we could keep going until it hits the ground. Remember, we're only thinking about what it's doing once it leaves our hands, right? Our hands aren't touching it. So the only thing that's acting on it is gravity. So it's accelerating in the y direction, right? but it's not accelerating in the x direction. So in the x direction, there's no acceleration. Vx is constant, and Vx is equal to the range. So if I draw that picture again, the range would be this. So Vx is equal to the range divided by the total time it's in the air. There's no acceleration involved because it's pushing forward at a constant rate. In the y direction, it is accelerating at negative 9.8. So the kinematics equations, Vf in the y direction is equal to whatever it starts out at plus gravity times time. Vf squared in the y direction is equal to Vi in the y direction squared plus 2g times its change in vertical position. Its height, or the height that it achieves, is equal to VIY times time plus 1/2 GT squared. And it's also equal to 1/2 of VIY plus VFY times T. So these are just the equations, and we're talking about just the y direction of motion, the up-down direction of motion, not the horizontal. So here's our summary of our equations, and this is the summary that you'll see in different texts. The x direction of motion, what determines how far it goes forward, is determined by the time and how fast it's moving forward. And then the free fall equations are the ones I've just written down for you. So let's say that you have a 200-meter high cliff, and you're going to fire a gun at 100 meters per second. It wants to know how long it's going to be in the air and what its maximum distance is. So the maximum distance is delta x. The only formula we have for delta x is Vx equals x times t. So we can't really do that until we know how long it's in the air. So what determines how long it's in the air? Well, what determines it is how high it is, and that is a vertical quantity, right? So we need to evaluate this in terms of what's going on in the x direction, okay, and the y direction. So in the x direction, it has an initial speed and a speed all the time of 100 meters per second. But in the y direction, it starts from rest. It drops negative 200 meters. Gravity is its acceleration. And we want to know the time in the air. So we need a formula that has VIY, Y, G, and T. And that formula, if you look on here, it's going to be this one right here. So I'm going to use Y equals VIT plus 1/2 GT squared. And remember that VI is 0. So here's the biggest mistake. This 100 meters per second is a horizontal speed. Horizontal. Straight means horizontal. So you have to imply in your brain that it's dropping from rest. So if I were to plug in my numbers, negative 200 meters equals 1/2 of negative 9.8 meters per second squared times time squared. I'm going to divide everything by half of that, which is negative 4.9 meters per second squared. And then I'm going to have to take the square root of that. So if I do that, I get 200 divided by 4.9. And then I just take the square root of it. And I'm going to get 6 time is equal to 6.39 seconds. Notice that if I had dropped a ball at the same time that I launched this bullet from the same height, it would be in the air the same amount of time. It would land exactly the same time as the bullet, but it would not land in the same place because the bullet is moving at 100 meters per second every second. So Vx equals delta x over t. So delta x is going to be equal to Vx times t, which is equal to 100 meters per second times 6.39 seconds, which is 639 meters. So our target has to be 639 meters away for it to hit it. At least if it's sitting further than that, it's not going to hit it. All right, what happens when projectiles are launched at an angle? Well, this is a little bit different, right? Because now we're going to give it some upward velocity and we're going to give it some forward velocity at the same time. So let's first consider what happens if we throw something straight up. So let's say we throw a ball straight up at 100 meters per second. At the top, its velocity is 0. And when it gets right back to where it starts, its velocity is negative 100 meters per second. So there's a symmetry here, and we have to know that there's a symmetry in the y direction. So this is Vyi, and this is Vyf for the whole trip. And remember, just like in problems, free fall problems, we can choose which part of our parabola we want to deal with. We can, if we want to know the time to the top, we would evaluate it from 100 to 0. If we want to know the total time, we're going to evaluate it from negative 100 meters per second. So in this case, Viy is 100 meters per second. Vy at the top is 0, and Vy at the bottom is negative 100 meters per second, and gravity is always negative 9.8 meters per second squared. So that doesn't change when we deal with something that has been launched at an angle. It still behaves that way in the y direction, and we still have our kinematics equations that we can use with this information. The only difference is that it is not just going straight up at 100 meters per second, it is also moving forward. So let's think about that. So if we launch something, let's say we now launch it at 100 meters per second at 30 degrees. So it's going to go up, it's going to come down right at the same height that it came from. So how does that look? Well, it's got a y component, and it has an x component. The y component is going to get shorter until Vy at the top is 0. And it's going to start falling down again, and when it hits the ground, it's going to have whatever Viy was, it's going to be negative. Vx is always going to be the same. So Vxi, Vxi, and Vxi. Always the same, even at the top. So at the top, it's only moving in the x direction. So how do I find those? Well, Vx is just going to be 100 cosine of 30, which is 87 meters per second. And Vyi is going to be 100 sine of 30, which is 50 meters per second. Vy at the top is going to be 0, and Vy at the bottom is going to be negative 50 meters per second, and gravity is going to be negative 9.8 meters per second squared. And there is no acceleration in the x direction, so Vx is always 87 meters per second. So let's do an example. So in our formulas, we have all this information here about how I found those things. A cannonball is launched upward at 30 degrees above the horizontal. So this is the same problem. So we found that it was launched upward at 50 meters per second. And we found that it was launched forward at 87 meters per second. Remember, Vy is going to be V sine theta. That's our initial Vy. And Vx, which is always the same, is going to be V cosine theta. So I just took 100 times cosine 30 and 100 times sine 30. If I want to find how high it goes, I'm going to use the y information. So let's look at what's going on in the x direction. X direction, Vx is 87 meters per second, and Vx equals delta x all over t. And in the y direction, for our first problem, Viy is positive 50 meters per second. V at the top is 0 because we want to find how high it goes. Delta y is what we're looking for. And g is negative 9.8 meters per second squared. So we need a formula that has Vi, Vf, y, and g in it. And that is Vf squared equals Vi squared plus 2g delta y. So remember that Vf is going to be 0 and Vy is 50. We never want to use the 87 or the 100 in this equation, which is the most common mistake made. I'm going to subtract Vi from both sides, so it'll be Vf squared minus Vi squared. Then I'm going to divide both sides by 2g. And that's going to give me my y. So I put all my numbers in here. It's going to be 0 squared minus 50 meters per second. That's supposed to be a 50 meters per second squared. All over 2 times gravity, which is negative 19.6 meters per second squared. I apologize for my big fingers. So 50 squared is 2,500 divided by 19.6. I can get rid of the negatives, and I'm going to get a height of 128 meters. Now I want to find how long it's in the air. Well, Viy is 50 meters per second. When it lands on the ground, the final velocity is negative 50 meters per second. Gravity is negative 9.8 meters per second squared. And t is what I'm looking for. So I need something that doesn't have x in it. That's going to be Vf equals Vi plus At. Subtracting Vi from both sides, Vf minus VI, and then dividing by A. So T equals negative 50 minus 50 meters per second divided by negative 9.8 meters per second squared. So my 50s don't cancel out because I'm subtracting a positive from a negative. So that's going to be 100 divided by 9.8, which is 10.2. And then in C, we want to know the maximum range. Well, the only formula we have that has range in it, delta x in it, is Vx equals delta x all over t. So delta x is Vx times t, which is 87 meters per second times 10.2 seconds, which is 888 meters.